So, hello everybody. Welcome to this week's Autonomy Talk. This week is a great pleasure to have Holger Caesar. Holger is a friend, and apart from that, he's a senior research scientist and the data curation team lead at Motional, which you might have heard as active autonomous mobility or nuTonomy. He is the project lead of the nuScenes dataset, which you might have heard of. And he has a lot of experience in organizing workshops and divulgation material for this kind of data sets. Before joining nuTonomy, Holger received a PhD in computer vision from the University of Edinburgh, working with Professor Vittorio Ferrari. Funnily enough, he was also a visiting scholar at ETH in 2017. And on a side note, if you happen to be in Singapore, Holger is the one that knows where all the good beer places are and all the good Singapore chili crab places are. So you should really use his knowledge for that as well. Today we'll talk about his work on data-driven development for autonomous driving, and we are all really looking forward to hearing this talk. So go ahead, Holger.
Okay, thank you, Joella, for the warm welcome. Yeah, it's always a pleasure to talk at ETH, as you already said. I was there as a visiting PhD student in 2017 for 1 year in the Mark Polyface lab. So it's always a pleasure to come back and talk to people. Today, I want to talk about data-driven development for autonomous driving. Of course, everything is data-driven in these deep neural network days, but I want to talk about it specifically from like the industrial perspective. The things that are maybe a bit different between academia and industry. Let's take a look at my overview. So first, I will talk a bit about our company. The name is relatively new, so some of you may not have heard it before. Then we talk about algorithms, some papers that we published, data sets, and then I want to talk more about data-driven development, and finally, some pitfalls. Okay, so let's start with what is Motional. So Motional is a joint venture between Aptiv and Hyundai. Both contributed 50-50, and the joint venture was valued at $4 billion. So of course, Hyundai, you all know, is a car maker from South Korea, and Aptiv is an automotive supplier from the US. Yeah. We have a lot of milestones, but roughly speaking, company called Aptiv acquired two different startups called nuTonomy and Automatica. Automatica is from Carnegie Mellon. nuTonomy is founded out of MIT. And then we kind of merged these together, and later the joint venture with Hyundai. Along that road, we had a lot of milestones. For example, 2016, where we launched the first public AV demo worldwide in Singapore. That was a pretty big milestone. But then also, yeah, there was a drive all across the US, first US cross-country drive. And then the first commercial AV pilot in Las Vegas. That is also a very big milestone. And nowadays, or in 2019, we released nuScenes, but also a quite popular safety white paper. So we try to kind of, give back to the community and share some of our insights. And yes, of course, in end of 2019, we had this joint venture. Okay. Our offices are primarily in the US. We have 4 locations in the US. Somehow the Los Angeles spot seems to be a bit wrong. And then we are also based in Seoul, South Korea, and Singapore. So personally, I'm based in Singapore, as Joella already said. Here is a video about our driving in Las Vegas. So I already mentioned that we have a commercial pilot in Las Vegas where we drive with Lyft. So you can use a Lyft app, call our cars, and they come pick you up. And it's basically 100 vehicles driving around the clock. And of course, COVID was difficult for all AV companies. But this is basically the video to announce that we're now back in Las Vegas driving with Lyft again. Let's take a quick look at this. I will not show play the sound, just the video. So this is our garage in Las Vegas. You can see lots of cars. can see the various sensors on our car. This is the Las Vegas Strip, where we drive between the various casinos and pick up people and drop them off. And of course, this is autonomous, but with a safety driver. Okay, that was the very quick introduction to our company. Now I want to talk about algorithms, specifically several papers out of our team. The first one is PointPillars, was published CVPR 19. So PointPillars is a LiDAR-based 3D object detection method. And when we started to work in that space, there was basically no LiDAR-based object detection method that worked in real time. There were some approaches that had decent performance, but not real time. So basically, we started out, we looked at VoxelNet was basically a state-of-the-art method, which kind of segments the LiDAR point cloud into voxels, learns the features inside these voxels, and then learns that in a standard neural network. And we looked at why this is so slow. And basically, we decided that these voxels don't really give you a lot of gain in autonomous driving. Of course, you can still have the 3D aspect, the height dimension as a feature, but you don't need to separate the space into voxels. You can just work with basically vertical pillars and learn the features inside those. And for an application like basically bird's eye view object detection, but also first person object detection, that is, works very well. And we also worked a lot on the feature encoding, tweaked that a bit. And then basically after these steps, you just feed that to a standard 2D CNN and a standard detection head like SSD. And that's why you get such fast performance, because these methods are really fast. SSD, yeah, much faster than VoxelNet. If we look at this, we see PointPillars on this curve. So this curve shows inference speed on the x-axis and MAP on the y-axis. And we see that PointPillars at the time that we published this was really slightly above the state of the art, but most importantly, much faster. So we achieve up to 100 Hertz. And in general, it's 2 to 4 times faster than the state of the art. So that was quite impressive, because that really enabled it for companies like ours to use these LiDAR-based object detection methods. The next paper was PointPainting. So it's a paper for sequential fusion for 3D object detection. And what we do here is we fuse LiDAR and vision camera features. We fuse them sequentially, and basically we combine the task of 3D object detection and semantic segmentation on the image. And that improves the 3D detection performance across classes, datasets, and also detection methods. Let's take a look at what that means. So here we have a LiDAR point cloud on the left side and an image. And the first step is that we run semantic segmentation on the image. We basically classify every pixel. Then we have these label maps. And now we project the point cloud onto the image and basically color the points with the labels. Then we have a representation like this. And then again, we just run our favorite 3D object detector, for example, PointPillars or PointRCNN, and then we get our predictions. So this is a very easy approach. And it's, especially if you think about a company like ours, which already has a method to do LiDAR detection and a method to do image-based detection, combining these two together is really comes for free, basically, and gives significantly better performance. Let's take a look at this. This is on the Kitty data set, and we basically took 3 methods, PointPillars, VoxelNet, and PointRCNN, and we see basically improvements throughout, except for one category in the PZ strata, but otherwise we see improvements everywhere. So this really works well. And on the test set, compared to various existing methods, we can see, of course, if we use this method on the existing state of the art, then we get even another improvement of 3%, which is very significant. Okay, that's on the prediction, on the detection side. Now let's talk a bit about prediction. This is a paper from our behavior modeling team called CoverNet, Multimodal Behavior Prediction Using Trajectory Sets. And basically, so the task here is also a task in nuScenes is you have 2 seconds of past data, and you are supposed to predict the pose of the vehicle in 6 seconds into the future at like half-second time intervals, time steps. And the approach that we took is to have sets designed to dynamically cover the feasible vehicle trajectories. We'll see what that means in a second. And that outperforms existing methods based on regression or ordinal regression of the trajectory. Let's take a look at how this works. So input representation is this funny image of the map. You see the various layers here, like pedestrian sidewalks, pedestrian crossings, lanes, etc. So it's all taken from nuScenes in this case. And then basically this encoding is somewhat arbitrary, right? So they chose to encode the orientation of the lane in terms of colors. It's quite clever the way they did it, but it's somewhat arbitrary. And then also the history of the objects is just encoded in terms of the brightness here of the box. So you can see that the past is a bit darker. So that's basically how they encode both the map information, but also the trajectories of the vehicles. So this is fed to a neural network. And in parallel, we also have the state of the ego vehicle, speed, acceleration, yaw rate, which is also concatenated with these features. And in parallel, we generate a set of trajectories. So here you see, basically, you can imagine the ego vehicle is at this position, and then we have all the possible trajectories in the current, from the current state. And then basically what this neural network does is it assigns a probability to each of these trajectories. Of course, they can be heavily pruned. To find the one trajectory, in this case, the green trajectory here, that is most likely. Yeah, that's the setup as I described a bit. The metric here is the hit rate. So a hit rate, top K means it's 1 if the top K prediction was always within 2 meters over a 6-second horizon, or 0 otherwise. And this, of course, a proxy for joint performance with planning. So let's take a look at this. We have a number of baselines here. The most simple, of course, being constant velocity and yaw. A number of other papers, I don't know exactly by heart right now what they do. But then if we look at CoverNet with different parameters, we see that the performance here is really much better, especially with larger K. As you can see, there's much more growth, whereas these baselines are almost constant. Okay, so that's a work on behavior modeling. This is another work which is still ongoing, therefore we don't have too many details here. It's called the reasonable crowd. And the idea is really that it's very hard to encode all the rules specifically for autonomous driving. Maybe it's much easier to just ask a crowd of reasonable people, ideally with driving experience, what they would do in various situations. So they created a number of kind of scenarios in simulation, and then they choose between different options of what the ego vehicle does to decide what is the reasonable basically choice to make. And basically the way this works is they have these scenarios, and then they have a number of rules, such as the distance to the sidewalk, the distance to other objects, etc. And then they want to learn a mapping from these rules or rule violations to the human preference. So that's a function as described here. And the goal is basically to learn this function. And in their case, they try to do it relatively easy, a linear function, such that you can really understand this model. So you could imagine basically the outcome could be the reasonable crowd decides a particular way because 80% of the relevance here came from the violation of the distance to the sidewalk, 20% came from the distance to another object, etc. So that's how we try to learn what reasonable behavior is for an autonomous vehicle. Okay, now let's look a bit about at data. So nuScenes was already mentioned by Joelle. nuScenes is a data set that we published in 2018, or the final release was in 2019. And if we look back at that time, we looked a bit at the literature, and there was basically only the Kitty dataset for 3D object detection. Kitty is a dataset from Germany, from Karlsruhe, and it is quite suburban. So you have typically low traffic density, not too many bicycles except for the few scenes that are downtown. It doesn't have 360-degree coverage, so the cameras are only facing forward. There's no radar data, etc. So we basically said that this is not sufficient. I mean, Kitty was a great data set when it was released, but for our purposes, it wasn't sufficient anymore. So we set about creating our own data set. And nuScenes contains 1,000 scenes, 20 seconds long each scene, with really the well-localized car calibrated and then synchronized across the different sensors. And the sensors cover the full 360-degree view. We have LiDAR, camera, and radar. We also have high-definition maps. You can see them over here. So we have 11 different layers from sidewalks, crosswalks, lanes, etc. We annotated all the 3D objects of 23 object classes in 3D. You can see that over here. And then, yeah, very important, also the license is free for research. Yeah. Other aspect of nuScenes is the diversity. So we carefully selected the scenes to make sure that they contain interesting maneuvers, rare classes, etc. The data is collected in 4 different locations in Boston and Singapore. And we basically have, of course, because Singapore is driving on the left-hand side, we have left-hand versus right-hand driving data, which is also a challenge. We have different vehicle and vegetation types because it's on different continents. And then we also made sure to include nighttime and rainy data, which at that time, no big data set had. So that's, of course, a unique challenge when you have these kind of glares here on your window, or rain on the ground. It's very reflective. A lot of challenges here. Here's a quick overview of the existing data sets when we released nuScenes. These data sets don't have any range data, so they were basically not very relevant for our purposes for 3D object detection. These were existing data sets, but as I said, they had various shortcomings. So then we released nuScenes, and basically afterwards, a number of other companies released very similar data sets. Some of them, like Lyft, for example, also use our code base in our format, which is great because it's compatible. And at the moment, I would say only Waymo is kind of competitive with our data set. They have the same number of scenes, but they used 5 times higher subsampling. So it's 10 Hertz instead of 2 Hertz. Therefore, these numbers look much higher, but it's pretty much the same. Yeah, but it's great to see that basically now there are a lot of companies out there which share their data and give it back to the community. Okay. So some people may ask, do we really need these ever larger data sets? And we ran that experiment, and of course the answer is yes. We need more data. Here we see on the x-axis the training data used for 3 different methods, SSD, PointPillars, and OFT. We can see this vertical bar here, which is basically the amount of data we have in Kitty. So it's maybe 25% of what we have in nuScenes. And then we see 100% is the entire train-well set of nuScenes. And the performance increases by 70% relative between Kitty amounts and nuScenes amounts. So there's a huge improvement here, and probably there would even be a bigger, more improvement if we had even bigger data sets. So we definitely need bigger data sets. Okay, so we released nuScenes 1.0. And after a while, we thought about, are there other things that we are missing? And we also got a lot of feedback from the community. And one thing specifically from companies was that not everybody works with 3D bounding boxes, 3D object detection. So 2D data set would also be very useful. So we created nuImages, which is a large-scale image dataset, 100,000 images, and every object is annotated with a 2D bounding box and a mask. And additionally, we added the past and future images and ego poses. So essentially, you can think of this as 100,000 video clips where the central frame is annotated in 2D. And then another data set that I like a lot is nuScenes LiDAR seg. So LiDAR segmentation basically means that you take the LiDAR point cloud and you label every single LiDAR point with a semantic label. In our case, we have 32 semantic labels. So we did this on the entire nuScenes data set, and in total, that's 1.1 billion points that we labeled by hand. And I think that's particularly interesting for one thing, because it gives much more detail than just bounding boxes. But the other thing that I'm very interested in is that we can now also focus on the stuff classes, which are these background classes like road, cycle, sidewalk, and building. Okay, here's a little example. Okay, quality is already high. So this is one thing from nuScenes with the LiDAR segmentation labels overlaid. We can see the teal color on the road. We can see green is terrain and vegetation. Then we have this kind of yellow here for buildings, orange for vehicles, red for other vehicles and bicycles, and blue for pedestrians. And you can see the level of detail here, and also pretty good quality in terms of registration that the points actually and calibration actually land on these poles. Yep, okay, that's an example. Okay, and given this data set, we also organized a number of benchmark challenges. So these were 3D object detection, 3D tracking, prediction, and LiDAR segmentation. And we have these about twice per year at various conferences. Of course, our favorite is always I-Do workshop. We just had it 2 days ago. Yeah, we basically try to keep the community engaged and always look for new benchmarks that we can set up. This is a slide I presented 2 days ago. It's from the latest detection challenge, but it summarizes the entire nuScenes detection task. On the x-axis, we see the timeline. So since the first baseline that we released until today. And we see LiDAR methods in blue, which have a high performance, and then, of course, no LiDAR methods, so just camera or radar or both have typically lower performance. And we see a number of milestones here. So one is PointPillars, which was our baseline. Another method was the winner of the first challenge was McVie's CBGS, which is very popular these days. Then we had our PointPainting for sequential fusion. In the second detection challenge, the winner was the Noir CVLab by Huawei. It's also a very good method, heavily assembled. And then these are the methods from the last challenge, the third challenge, where Centerpoint V2 was the winner. And what I find very impressive is that in 20 months that we've been running these challenges and the task in general, we saw an improvement of 26% on NDS, which is our nuScenes detection score, which I'll talk about later, and 36.6% improvement on MAP, which is really a giant improvement. Okay, now let's talk a bit about data-driven development. So a data-driven pipeline could be thought of as we have our drive logs, our records from the driving in the car. Then we randomly sample data from that. We put it in our bucket. Then we manually annotate this data, create an annotated database, and then we train our ML algorithm for object detection, for example. Now, what if we need stronger performance? Well, it's as easy as ABC. A, we draw more samples. B, we annotate more data. And then C, we train a new model. And basically, we can keep on looping like this forever. But of course, there will be somewhat diminishing returns. So maybe we can do this more cleverly than just adding more data. And it turns out we can. So one thing that we can do is active learning, actively sampling the data points that we want to annotate. So this is basically using a neural network to look at the data, measure uncertainty of the network on this data, and then pick the samples with the highest uncertainty that we want to annotate. The next thing is automated annotation. So of course, we can use this network to label images, and then we can use these labels. In the fully automated form, I'm not so convinced yet that that works well, but we can do weekly supervised, we can do semi-supervised. There are a lot of different approaches that we can use here to make that work. And then finally, when we have all of these annotations, we probably do want to refine these annotations rather than just have these old erroneous annotations sit there. Specifically in our context, when we update taxonomies and conventions change and so on, it's very important that we detect such inconsistencies and that we kind of try to go back and fix the old data to be compatible with the new conventions. Okay, let's talk a bit more active learning, specifically at the literature for active learning. So as I said, active learning is we want to flag interesting samples for annotation. There are a number of different approaches for that. You can measure the disagreement between different models. This is typically called ensembling. You can measure the disagreement between the same model, but with different randomness. This is using Monte Carlo dropout. You can measure the disagreement between the same model from different viewpoints. This is a very recent paper called Viewpoint AL. You can measure the disagreement between the same model across time, basically checking for temporal coherence. And then the last method is a paper which is quite interesting. It performs loss prediction. So there's an extra output, an extra head, regression head attached to the network, which predicts the loss of the network on a given image. And then this loss can be used as a measure for uncertainty to say which images should be annotated. This is kind of a quick literature review. We also have a number of internal works, but unfortunately they're not published, so I can't talk too much about those. And then what's really essential, of course, is metrics. So traditionally, in our field, most people work with position and recall-based metrics, such as mean average position, which is, of course, integral over the recall position curve, averaged over classes. That is a good metric, but it's very generic, and it doesn't tell us too much about what the source of improvements is. Then there are a number of domain-specific metrics. So one is by Waymo in their dataset paper. It's called mean average position weighted by heading, and it's very straightforward. And you can imagine that that is quite relevant, that the vehicles in front of you are more important than the vehicles behind you. But you could, of course, add that other factors like distance, for example, are missing here. And then we created this nuScenes detection score. So that's the main metric in the nuScenes benchmark for object detection. And it's basically just the weighted sum of MAP, but then also the errors on true positive errors on translation, scale, orientation, attribute, and velocity. And we like this metric because it really helps you to disentangle the different factors, the different types of errors. Whereas in IOU, therefore MAP, you have basically translation, scale, orientation, all mixed together into one metric. And you don't know what the problem is with your method. And then lately, there are neural planning metrics. So we collaborated with people from NVIDIA. They created this metric called PKL, which is planar KL divergence. So the idea is basically they use the predictions of an object detector, and then they compare how similar is the planned route given the predictions to the planned route given the ground truth boxes. And this, the KL divergence between these two is a measure for how good the predictions are. And the beauty here is really that you don't need to handcraft your metric. It's basically an end-to-end metric which measures the performance of the planner rather than just of the perception system. And as I said, we partnered with them. We created a workshop paper which, analyzes this metric in detail, specifically on the nuScenes detection challenge. Analyze in general, it correlates pretty well with MAP, but on the finer scale, you can see some differences. Also, some situations where it's better. Yeah, so it's a very interesting metric. Okay, then we also did a partnership with a company called Search, which is also founded by former ETH students. So basically, what Search does is they index datasets, and then they provide you with all these interfaces to query them and basically discover your dataset. So we did that with nuScenes, and it's available for everyone, researchers, for example. And you can look at this platform here, some examples. So you can see the velocity, you can filter by velocity, you can filter by classes, you can filter by map locations. So hundreds of different things that you can filter. Scenarios, for example, the car is driving at a certain speed, doing a certain lane change. Yeah, so it gives you interesting insights. And I think such tools are very important. Of course, we're also building them ourselves within our company. But to really do data science, you need to have these good tools. Okay, now I would like to talk about some pitfalls while doing this data-driven development, or specifically in our case. So one big message is that algorithms can be changed, but data is there to stay. So if you work in a company, changing an algorithm usually maybe takes one person a few months, but it's very feasible. Whereas if you want to change your entire data set, that probably takes years, and it's millions of images that you need to relabel. So those decisions stay around. And some questions that you need to think about are, for example, how do you label data? Do you label it modal or amodal? Here, modal means that basically every visible pixel is labeled, whereas amodal means that also the non-visible occluded pixels are labeled. And there are different ways that people do it. I think most people do segmentation in a modal way, although there are papers that do it amodally. But then for bounding boxes, there are different groups of people that do it differently. In nuScenes, we work with amodal bounding boxes, but in the traditional, especially 2D object detection data sets, it's always modal. So that's an important decision. Do you want to detect whether the entire extent of the car or just the visible parts? Then there's the question, of course, what do you annotate? Do you annotate 3D boxes, 2D boxes, masks, points, the map? Probably if you really want to build autonomously, because you need to annotate all of them, but maybe there are also synergies between these different types of annotations. So for example, between 3D and 2D, of course, you can project 3D boxes to 2D, but then they are generally not tight, so you may want to adjust them manually. Then questions like, do we annotate bikes and riders as one object together or as two different objects? So if there's a bicycle with a rider, do we need two bounding boxes? My opinion here is that I prefer to have everything as one bounding box, because otherwise you need post-processing steps where you basically associate those two boxes, which is also tricky. But of course, you could model that in your network as well. And then the question, how do we deal with missing labels? So my preferred option that I've followed in several data sets is to use an other class. So you could have like vehicle other to kind of contain all of these generic objects that you didn't think about, that you have never seen before, but that are somewhat different from other classes that you have in your data set. Okay, and then of course there are difficult annotation decisions everywhere. So for example, how do you annotate these two adults carrying this log? Do you annotate just the adults and ignore the object in the middle? Do you annotate them both together? Or do you annotate them both separately and make the cut close to one of them, which is also somewhat arbitrary? So these are very difficult decisions, and you need to have very clear guidelines how you want to annotate these. Then, of course, weird shapes are everywhere, especially if you drive in Asia. There are lots of challenges, and in general, every country has its unique challenges. And even when we go to a new city or a new part of town, we really need to see what are all the challenges there. And then this is a little story from something we experienced. So we years ago, we trained an object detector which had a pretty solid MAP, and then we rolled that out with our team car. They collected some data, and then they came back to us saying that these very close pedestrians were not detected at all. So we looked into that, and what was the problem? Of course, we didn't have any data of close pedestrians in our data set. It only looked like this normally. So that's something you need to specifically take into account, that sometimes the pedestrian may actually even lean over the sensor, so they will be huge. So you need to take that into account during training, but also during testing, that you basically check for all of these corner cases that you are familiar with, whether you have decent performance on those. Yeah, of course, if you do object detection, you will have plenty of false positives, such as pedestrians in the trees or bikes pretty much everywhere. Yeah, I think the blue boxes are bikes. Yeah, and we'll find lots of exotic corner cases that you need to take care of. Yeah, so as a conclusion, algorithms are essential, and we require very good benchmarks to quantify their performance. Data is essential. It should be shared and standardized and benchmarked or used for benchmarking. Data-driven development provides a path to better models. And metrics are, of course, essential because we need to solve the right problem, not just some proxy for it. Automating this cycle is very important research direction, and very ongoing research direction that we are very interested in. And then data decisions have a long-lasting impact in a company. And of course, corner cases abound. So that's the end of my talk. I'd like to thank all of our co-authors and colleagues for their work. And if you are interested in joining us, you can contact either me or take a look at our homepage and look for jobs there. Okay. Are there any questions?
Thank you, Holger. Great talk. Are there any questions from the audience? If yes, simply unmute yourself and feel free to ask.
I have a question, maybe. First, yes. For the algorithms, for example, for the point pillar algorithm which you mentioned, do you have a model architecture open source, for example, in PyTorch of your model, or do you have even a pre-trained model already open source, which can everybody use?
Mm-hmm. That's a very good question. So for PointPillars, we did release our code. The thing is that the code, you can reconstruct the results from the paper, but it wasn't really maintained. So after a while, we discovered another repository, which was the second paper. They had a nice repository, and they implemented a number of related papers such as PointPillars. So then basically at some point we started pointing everyone towards this repository. And it was a similar story since then. So MacV's CVGS, they created a nice repository, which has at least a handful of methods, maybe more. And very recently there's detection from a very diverse group from Singapore and China. And they support, I think, 60 different methods, 5 data sets. So they basically created a repository that can do certainly PointPillars. I'm not sure about PointPainting. I think that's not implemented. But it's, of course, very easy to do, right? If you have semantic segmentation and LiDAR, like 3D object detection, then it's very easy to combine those two yourself. So the answer is there are some repositories, but yeah, nowadays we mostly point people to other third-party repositories.
Great, thank you for your answer.
Hey, thank you for the talk. I was wondering, since you, especially in nuScenes, you have different environmental conditions, is there something you do to account for, like, let's say, unbalanced number of data points in different domains? Just like there are methods for different classes. Is there something you do to account for that? Like exactly like in this picture here?
Yes, so one of our highest priorities is to find rare classes. And rare classes is not just, the ice cream truck or something. Even bicycles are very rare. If you look at Kitty or nuScenes, in general, there are not enough bicycles, and bicycles are hard to detect. So we do a lot of mining, which is basically active learning, but you can do it in a very simple way, right? You just run your object detector on a lot of data, and if there's a bicycle anywhere, then you try to label that data. So that's how we try to get these rare classes. Of course, then there are many other aspects of diversity, and we try to kind of manually balance most of these things. So we have the different cities, we have the 4 different locations, different routes in those locations. We looked at the map coverage to make sure that it's not just all in like one area. And then also night data and rain data. We basically said we want like maybe 15–20% of these, such that it's a healthy ratio, but it's not dominating the data set.
All right, thank you.
Other questions?
Yes, from my side. So first of all, thank a lot for the nice talk. I would have a little bit more unusual question about your data infrastructure, data architecture. You mentioned you do a lot of active learning to sample data from this large unlabeled data set to get more insights. Could you talk a little bit more about what underlying architecture you're using for the servers where you store the data? Is it something like an object-based storage, or is it simply a test drive mounted somewhere? How do you do that, and how many models run there in parallel?
It's an interesting question. I'm certainly not an expert at that. So most of our data we get from the cloud, AWS services like that. So it's being stored in the cloud. Of course, that comes at significant costs. So we do try to have as much processing as possible, let's say in the garage where the car returns to. Of course, on the car is the next step. So there, basically these different tiers of processing and also storage on the car, then in the garage, then in the local data center, and eventually in the cloud. But when it gets to us, usually at that point, we would get it from the cloud, which is more universally usable. In terms of the actual systems being used, I don't think, well, first of all, I don't know too many of the details, and second, I'm not sure if I can share them. But maybe, yeah.
Sure. Just one small question. When you talk about the cloud is expensive to use, you mean because you have to pay the computation hours, or because it's slower than the on-premise prediction or on-premise computation?
So even just the data storage, if you think about a fleet with, as I said, in Las Vegas now, the public fleet is maybe 100 vehicles. But if we go to tens of thousands of cars, you can't even store all of that data, right? It's terabytes per hour, and then we drive the entire day. So you can't even store all of that data. So already at that point, you need to think about maybe 5% or so of the relevant scenarios we store, and the rest is just getting deleted after some time. And then, yeah, that's only the storage. So only the storage is already too expensive. And then if you go to processing, it gets, of course, much more expensive. So in general, I think, yeah, the compute on the car really helps you, because we run all of our networks, of course, on the car. We can run active learning on the car, and then we just store that in the cloud. And then indexing that is much easier than if you were to rerun a neural network on the entire data set.
Yeah, that makes a lot of sense. Thanks a lot for the explanation. Yeah,
it's a tricky topic, and it's hard for anyone, I think, to get a good overview of that. Of course, also a lot of confidential proprietary information there.
Yeah, thanks a lot.
Good. Other questions?
I have a question, Holger.
Yeah.
So a lot of the audience is PhD students, and some of them are starting out now. So they'll be graduating in 3-4 years, 5, 6, 7. Let's not put limits there.
Mm-hmm.
And so I think a good question is the following. What is something that you guys in the industry really have no idea how to do? Because that's kind of the, a good topic for research, right? So that these guys can think about it for 5 years and then, provide a solution to you in 5 years.
Yeah, it's a very interesting question. So I would say it already starts with active learning that we just talked about. I briefly mentioned 10 different methods, but the truth is if you try them on various different data sets, many of them will only work on 1 or 2 data sets and they will give you a 1% improvement or so. It's still very far from what we really need to solve these questions like, what data do we store, what data do we annotate? So there's still a lot to be done there. Then also semi-supervised methods, I think, are not working that well yet. So, we have all this vast amount of unlabeled data, but the truth is that most of these companies can't really use it very well. Of course, you get some increase in performance, but I think much more needs to be done there. But that's only the topics I talked about today, right? I think in terms of new sensors, there's a lot of very interesting stuff coming. 3D radar, LiDAR with Doppler LiDAR, basically. Ground scanning sensors. Like there's so much more there that we're not using. Event cameras, but basically at the moment, most autonomous vehicles are just radar, LiDAR, camera. I think there's much more to be used there, which I think that could be one of the biggest increases in performance once we roll out these new sensors. Yeah.
Thank you. We should also mention that, I don't know if you mentioned the internships, right? But I'll let you say it, right? So you have a lot of ETA interns there, right?
Yes. We have a very vibrant community, especially from the, what's it called? Formula One, Formula AMZ team. Yeah, so we do really like our ETH interns, and a lot of them actually stay with us full time, or some of them come back every other year for another internship. So yes, if you are interested, just reach out to me. And we are in, as you saw, in various locations. So from California to Singapore, if you have preferences, so we can talk about that.
Thank you. Is there any other question?
Maybe I have another question. I don't know if you read my email. Maybe you can also discuss it offline as you want. But
maybe you phrase the question assuming that I haven't read it. I only briefly looked through the email so far.
Yeah, in general, we are working on sensor selection. So how to find the best sensors for in autonomous driving for a specific task. And thereby, on the one side, we need to find specifications from our sensors for our task, but then also use these specifications to find out what is the AD performance at the end of these when you're using these sensors. For example, what is the safety or the comfort of the driver class? Maybe if you think about emergency braking. So thereby, for the sensor specification, we need much more than just a mean average precision. We need, for example, the false positives dependent on the object distance, or maybe the velocity of the vehicle. And so one idea was that we used the nuScenes datasets to get such statistics. Do you see any limitations or something which you need to pay attention when we find such statistics? And for example, when we think about the velocities of the vehicle, which we get from the data set, is there a velocity predominant, or can we build clusters such as, I don't know, 15 kilometers per hour, 30, and something like that?
Yeah, so I do think among the existing data sets, nuScenes is the best data set. But I also think that for this question, but I also think there are a lot of limitations here. In that, if you look at very specific subset of the data, say all the cars driving were at more than 10 meters per second, that they will be very heavily biased, right? than you are maybe on those two very big roads with 4 lanes. So it's very difficult to make general conclusions out of that, especially if you think of like, if you look at object detector performance. So I often look at like performance of on the night data, on the rain data, on the normal data, Singapore data, Boston data. And some conclusions are obvious and other conclusions are almost surprising. And often I think the surprising ones are mostly due to the different data distribution. So for example, at nighttime, there are much fewer objects out there. They are almost exclusively cars. We have very few pedestrians or bicyclists out there. And then, yeah, of course, yeah, the performance is also very different. So I think these are really, they will make it harder for you, these kind of different data distributions to really get a good conclusion there. But I think it's a very interesting topic, definitely.
Okay, great. Yeah, probably I need to check out CR search, which you mentioned during the talk.
Yeah.
Thank you very much.
Thank you.
Are there any final questions? If not, I think Holger gave his contact. So if you feel you have deeper questions, you can, I assume you can contact him.
Yes.
Thank you very much, Holger. It was a great pleasure hearing again some of your recent developments. And thank you very much, everybody, for participating. See you next week to the next Autonomy Talk.